In this last section, what we want to do is talk a little bit about vectors again, and this time it's vectors from the algebraic point of view. So I've written some definitions over here. First of all, for the two unit vectors that we're going to use. I is the unit vector that goes from the origin 0, 0 out to 1, 0. So it's 1 unit long, and it's exactly horizontal like this. So it points from the origin and moves out to the point 1, 0. And that's the unit vector I, and we call it the unit horizontal vector. The unit vector j is the vector that goes from the origin to the point 0, 1. So the unit vector j is the unit unit vertical vector, and it points straight up. So that's the vector I, and that's the vector j. Now, algebraic vectors look like this. If we have a vector v that starts at the origin and goes out to any point a, b, then we can write v as a linear combination of I and j. That is, it's a times I and b times j, where I and j are these two unit vectors that we've defined right here, and a and b are the coordinates of that ordered pair. Now, the magnitude of this vector v is a squared, square root of a squared plus b squared. So you simply take those coefficients and take the sum of their squares, the square root of that gives you the magnitude or length of that vector. Now, here's an example. The vector that goes from 0, 0 out to the point 2, 3 is the vector 2i plus 3j. And I think you can see that right here. If it starts at the origin and goes out to the point 2, 3, that's a vector that's 2i units long this way, plus another vector that's 3j units long this way. So if I add 1i plus 2i, I get this vector, and then if I add to that 1j plus 2j plus 3j, you can see I'll end up at this point. So this vector right here is the sum of these two vectors plus these three vectors. So it looks exactly like the vector v is 2i plus 3j. So this algebraic method of working with vectors puts vectors into a condition where we can do some of the things that we have done in algebra with polynomials and that. So we want to take these definitions here and work a couple of problems. Let's look at our first one. We want to draw the vector that goes from 0, 0 to 4, negative 5, and then I want to draw it, and then I want to write it in terms of the unit horizontal and vertical vectors. So the vector that goes from 0, 0 out to x equal 1, 2, 3, 4, y equal 1, 2, 3, 4, 5 is going to be, now let me get my ruler here and draw that vector nicely if I can. So that vector is going to look like this. So that's this vector that goes from 0, 0 out to the point x equal 4, y equal negative 5. Now you can see as far as adding vectors to get that vector, it looks like 1i plus 2i plus 3i plus 4i, that's 4i, and then I have negative 1, 2, 3, 4, 5j to get down there. So that's negative 5 of those unit vector j's. So this vector v that goes from the origin to 4, negative 5 is written as 4i minus 5j. Now there's another way that we write these vectors, and that is with these brackets that look like this, where we just write down these coefficients, 4 and negative 5. So 4i minus 5j is the same as this notation right here in vectors. Now let's look at the magnitude of this vector for a second. The magnitude of v is going to be its length, which is the square root of this distance squared plus this distance squared by the Pythagorean theorem. So it's 4 squared plus negative 5 squared. That's going to be the square root of 16 plus 25, which is the square root of, let's see, 41. But I think you can see that by the Pythagorean theorem, this is a right angle right here, so the length of this hypotenuse right here is the sum of the squares of these two sides, and this side has a length of 4 and this side has a length of 5. So doing vectors algebraically like this is really pretty simple. If I want to draw the vector that goes from 0, 0 to 4, negative 5, it looks like this, and I can think of that as being 4i plus another negative 5j, so I write it that way. This is a notation that we use in the book that means the same thing, and then if I want to find the magnitude of this vector, I use the Pythagorean theorem just like I have in the past, and it's just the sum of the squares of the two components, these two numbers right here, and the square root of all of that. So now let's go on and look at the magnitude of a couple of other vectors. Okay, so I want to take the vector w, it's 5i minus 12j, and I want to find its magnitude. Well, the magnitude of w is simply going to be the square root of the I component squared, sometimes called the horizontal component, plus the vertical component squared. So square root of 5 squared plus 12 squared, that's the square root of 25 plus 144, which is the square root of 169, which is 13. So this vector, 5i minus 12j, has a magnitude of 13. So that's the length of that vector. Now this vector right here, negative 5, 6, remember that stands for negative 5i plus 6j. So that's what that vector looks like if I write it with in the component form like this. Well, the magnitude of negative 5, 6 is the square root of negative 5 squared plus 6 squared, which is the square root of 25 plus 36, which is the square root of, let's see, 6 and 5 is 11, so what? 61, square root of 61. So there you can see, as far as finding the magnitude of these vectors right here, it's really a pretty simple process. It looks just like the Pythagorean theorem, and as a matter of fact, it is based on the Pythagorean theorem. So what we want to do next then is look at addition and subtraction with these new vectors that are written in algebraic form. So let's take a look at our next problems. So if u is equal to 2i plus 5j and v is equal to 5i plus 2j, let's find the sum of u and v. Well, with algebraic vectors, that's really a simple process, and it looks like this. It will be 2i plus 5j, that's u, plus v, which is 5i, plus 2j. Now we add, just like we would add similar terms. This will be, let me just collect these here, 2i plus 5i, plus this is 5j, plus this 2j. So I think you can see pretty simply that's just going to be 2i plus 5i is 7i, plus 5i plus 5j plus 2j is 7j. So the sum of u and v turns out to be a vector in component form 7i plus 7j. So you can see I have 7i plus 7j as the sum of these two vectors here. Now the next problem I want to do, I want to multiply u by 3 and v by 2 and find that sum. So let's take a look at it. So 3u plus 2v. So this is going to be 3 times u, which is 2i plus 5j, plus 2 times v, which is 5i plus 2j. So this is just the distributive property. 3 times 2i plus 5j is going to be 6i plus 15j, plus 2 times 5i plus 2j is going to be 2 times 5i plus 2 times 2j, again just by the distributive property. So I'll have 10i plus 4j. Now I'm going to add my horizontal components. 6i plus 10i is going to be 16i. And then I'm going to add my vertical components. 15j plus 4j is going to be 19j. So what I get for the expression 3u plus 2v is 3 times this vector u plus 2 times this vector v, and that really amounts to just multiplying like we did with the distributive property in algebra. So I get 6i plus 15j, here I get 10i plus 2 times 2 is 4j. Now I add my i's together and I get 16i, I add my j's together and I get 19j. So working with vectors in algebraic form, addition and subtraction with vectors and this kind of scalar multiplication right here is really pretty easy.